Now before we do example 10.8.3, let's take a look at this little formula here. The area bounded by two curves can be found using integration. So this is like in the following example, an area trapped between two curves. So the area can be found by working out f of x take away g of x, where in this formula f of x is the top curve, so the one that is higher up, and g of x is the bottom curve. Take them away and then integrate between limits of a and b. Now this formula only works if the two curves do not intersect again between a and b. So they can intersect at the beginning. They don't have to, but they can intersect at the beginning, intersect at the end, that's fine. But if they intersect again in between, this won't work. If you take a look at the diagram on the top right corner of the screen that has just magically appeared, this is an example of where it would not work. So between limits of a and b, if you did top curve minus bottom curve, well, we can't figure out which one is always on top and which one is always on bottom because the curves have intersected between a and b. So this is an example where it would not work. So going on to example 10.8.3, R is trapped between the two curves. I'll just repeat again, they do not have to intersect at the beginning and at the end. Okay, they don't have to. I'll do a quick example diagram. So between A and B, it is possible that they don't intersect between A and B, and we can still do top curve minus bottom curve to find the area. So that's an example of where we could still do that. If this was f of x and that was g of x, they don't have to intersect at A, they don't have to intersect at B. You'll find quite often they will, but I'll just say it one final time, they don't have to. So looking at the diagram, the top curve is f of x, and we're told f of x is sine 2x, and the bottom curve is g of x, which is sine x, multiplied by the square of cos x. On the diagram, x goes between 0 and pi over 2. The region R is bounded by the two curves, as we can see in the diagram. Use integration to find the area of R. It's useful to know that it doesn't matter whether R is completely above the x-axis or completely below, or maybe a little bit above, a little bit below. It actually absolutely does not matter. When you're doing top curve minus bottom curve, it doesn't matter where that area is on the graph. You might have a little bit below the x-axis, a little bit above. We don't need to worry about it, so that's good news. So here we go. The top curve is sine 2x, and the bottom curve is sine x multiplied by the square of cos x, which I'm writing in a slightly different form. I just want to make sure you're fully aware these two notations, they mean the same thing. So that's top curve minus bottom curve. Limits, well, the area begins when x is 0, so that's the lower limit, and the area finishes when x is pi over 2, so that is the upper limit. Now earlier in the video I said take away the two curves, f of x take away g of x, and then integrate. However, only do that if they have any like terms. In this particular example, taking them away is not really worth trying to do. If f of x and g of x were polynomials, so for example they had constant terms and x squared terms and so on, then they'd have a lot of like terms. Taking them away will be much easier. Here there's no point trying to actually take these away from each other. We've just got two individual terms and both of them can be integrated immediately. The integral of sine 2x is minus a half cos of 2x. We can check that by imagine differentiating minus a half cos 2x. See what you get. You should find you get sine 2x. Now integrating the second term. Now you might be able to do this immediately. If not, that's fine. I'm just going to go on the right hand side now and let's try cos x all cubed. I've noticed we have cos and it's squared, and we have something like the derivative of cos next to it. So this fits the pattern of having a function to a power and some multiple of the derivative of that function right next to it. So that's why I'm trying cos cubed x. You'll see when I differentiate cos cubed x why I decided to try that. So we've got to use the chain rule here, multiply by the power, take one away from the power, and then multiply by the derivative of the inside of the brackets, which is minus sine x. So we've got the cos squared x that we need. We've got the sine x that we need. We've even got a minus there as well if we want to include that. The only thing is what I got was 3 times too big. So therefore I can fix that by making my original trial 3 times smaller, and then it's exactly right. So now I know that the integral of the second term is 1/3 multiplied by the cube of cos x. However, I need to be very careful here. Going back to my trial, when I differentiated a third cos cubed x, it generated a minus. So if I left my answer like this, then imagine differentiating this to check it. It would generate another minus to go with the one that's already there, which would of course turn into a plus, but we need it to be a minus. So therefore this needs to be a plus. I'll just say it again, we can check that by differentiating it. If we imagine differentiating 1/3 cos cubed x, and I'm deliberately including the plus here, so I'm differentiating positive 1/3 cos cubed x, just like I did over here, then that generates the minus that we need to see in the original integral. So all remains now is to get the limits substituted in. I would always recommend putting these important brackets in first, especially when we have more than one term inside the square brackets. So we've got 2 terms here. These second pair of brackets are absolutely crucial. The first pair not so much, but I'm just doing it for symmetry. The second pair absolutely vital. So carefully sub the limits in. Top limit in first. The first term is a half, the second term is 0. Now the bottom limit. Just like in the previous example, don't jump to the conclusion that you will always get 0 when you substitute 0 in. For the first term, cos of 0 is 1. So the first term is minus a half. And again in the second term, cos of 0 is 1. So the second term is 1/3. So this is 1/2, and by expanding the second pair of brackets, plus a half, but take away a third. So that's a whole, take away a third, which is 2/3. So the exact area of R is 2/3.